In the previous video, we learned about the three major types of bonds that occur between atoms. And in this video, we're going to kind of follow up with the additional information that we need to know about bonds. One thing that we mentioned in the previous video is that when you bind together atoms with bonds, you make these larger structures. One category of these structures that tends to be really important within biology are structures called organic compounds. So a lot of times when we tell people like organic, they're like, oh yeah, I've heard about organic. That basically means that it's naturally occurring. No. A lot of, that's what it mean if you go to like a farmer's market and you're eating produce. But if you're talking about molecules and compounds, that's not what this means, because there's a lot of naturally occurring compounds and molecules that are not organic. What makes a molecule or a compound organic is that it contains carbon. That's kind of the key feature, is the presence of carbon as the backbone of that structure. And that carbon is typically going to be bound to oxygen, nitrogen, and or hydrogen. If those four elements sound familiar to you, it's because those four elements are the big four that together make up 96% of living organisms. And they're usually held together with some type of covalent bond. Now, you can get a lot of different organic structures because carbon is a very versatile molecule to act as a backbone. And it's so versatile because it can make 4 covalent bonds, which gives it a lot of possibilities in how it can bond to other atoms. Now, these organic molecules that we're talking about are usually rather large. And so we've kind of come up with an abbreviated way of showing the structure of these organic compounds. Instead of drawing the letter C, which is the elemental abbreviation for carbon, in the structural formula, we basically create a structural formula where we do not add carbons or hydrogens that are bound to carbon. So for instance, if I was going to redraw this piece of the structure in the unabbreviated format, anywhere that 2 lines come together, or where a line terminates and there's nothing else, is where there's going to be a carbon atom. So if I was going to redraw this apex right here would be a carbon, and it's bound to oxygen, which is then bound to hydrogen. This carbon is bound to another carbon, which is this one right here. Then there's a double bond between this carbon and the next one, hence the 2 lines in the picture. And then that carbon would be bound to another carbon, which then is in a carbon ring, okay? And then we know that carbon likes to make 4 bonds, so any additional bonds that we don't see are made to hydrogen atoms. So this carbon has 1, 2, so there must be a hydrogen there, and a hydrogen there. This carbon is currently making 3 bonds, 1, 2, 3, so there must be 1 hydrogen that's not shown. This carbon is likewise making 3, so there must be 1 hydrogen not shown, and so on and so forth. So if you see structures that look like this, where it basically just looks like a ton of lines, it's an abbreviated way of showing organic structures, organic compounds. And again, where 2 lines come together, or where a line terminates, and if there's nothing else listed, those are all places that carbon atoms exist. Okay. The bonds that form between atoms are able to be broken and reformed. Kind of as we talked about in the previous video, the amount of energy that it takes to break them differs. You know, those nonpolar covalent bonds require the greatest energy input to be broken, but technically, if you have enough energy, any bond can be broken. What we find is that bonds are broken and new bonds form to create new molecules in events called chemical reactions. So chemical reactions occur when bonds within molecules and compounds are broken and are formed to make new molecules and compounds. What we see with chemical reactions is something that looks like this. What we do is we have an arrow, and the arrow signifies the occurrence of the reaction. And this is the abbreviation for reaction, RXN. So anything that's to the left of the arrow is what's present before the reaction occurs, and anything that's to the right of the arrow is what's present after the reaction is done. The things that are to the left of the arrow that we have prior to the reaction are called reactants. And the things that are to the right of the arrow that we have after the fact are called products. In order for the chemical reaction to occur, all reactants must be present, and they must be present usually in certain quantities. It's very much like making a recipe. If you're going to make a recipe of chocolate chip cookies, you have to have all of the listed ingredients, and you have to have them in the correct ratios. So for instance, if you're missing chocolate chips altogether, then you're not going to be able to make chocolate chip cookies. Even if you only have like 3 chocolate chips, but you have like 10 sticks of butter, you're not going to be able to form the recipe that's stated and truly make a chocolate chip cookie. It's not enough to have double of one if you don't have an adequate quantity of the other ingredients. And the same thing is true of reactants. They need to all be there and in the correct ratios for the chemical reaction to progress. Now, ultimately, at the end of the day, when these chemical reactions occur, we're not really making any new matter. What we're doing is we're rearranging these atomic building blocks to make new structures, but we haven't created new building blocks or destroyed them. This is something that we know in chemistry that's called the law of conservation of matter. This essentially means that matter is neither degraded or destroyed. If we take inventory, all of the types and amounts of each element that are present beforehand are also present after the fact, potentially just ranged into new combinations. So for instance, if we look at this example, on the reactant side, there are 3 oxygen atoms, there is 1 carbon atom present, and there are 2 hydrogen atoms that are present. If we look on the product side of the reaction, we have 3 oxygens present in carbonic acid, we have 1 carbon, and we have 2 hydrogens. So even though we've made a new structure by changing where bonds are formed, we haven't changed the atomic building blocks that are present. So chemical reactions are really critical. They're happening constantly inside of living organisms. And these chemical reactions have to occur at a certain speed in order to maintain life. Okay, so there's definitely going to be times where the speed of the chemical reaction is critical. So we need to know what can ultimately manipulate how fast these reactions occur. One thing that can change the speed at which a chemical reaction happens is the amount of the reactants. Typically speaking, if you increase the reactants, then you can increase the speed of the reaction. The reason why has to do with the fact that in order for the reaction to occur, the reactants essentially have to collide into one another. They're kind of moving around randomly in space, as you can see in my beakers, although this is really kind of intended to illustrate the next point. And they're kind of just bouncing around very erratically in whatever space they are contained within. The more reactants there are, the more likely is for collisions to occur. So then your reaction is more likely to happen. Changing temperature is also something that can affect the rate of the reaction. Technically speaking, if you increase the temperature of the system, then you are going to increase the speed of the reaction. In terms of why, well, ultimately, what temperature is temperature is going to measure the amount of kinetic energy in the system that that substance possesses. And the kinetic energy is the energy that is associated with motion. So if something has more kinetic energy, then it's going to move faster. We can see that happening in the animation that I made here. Right here, we have a warmer system. There's more kinetic energy, and the individual reactants are moving around faster in the space of their container. Because they're moving quicker, it doesn't take as much time for them to collide into each other and create a new molecule, which you eventually see once they connect together. Over here, where it is a lot colder, everything is moving a lot slower. It's not to say that they won't collide eventually, but it clearly seems that it's going to take a while, and therefore it's going to take a while for the chemical reaction to progress. We're not going to talk about it a lot right now because it's really going to be something we hit on later, but there are actually specialized structures or proteins called enzymes, and enzymes themselves are intended to speed up chemical reactions. So typically speaking, if you add the correct enzyme, then you're going to lead to an increase in the speed of the reaction. And again, we'll touch more upon enzymes in a later module. We've spent time now talking about bonds that occur between two atoms to make a molecule. So the ionic bonds we talked about, the covalent bonds we talked about, those are bonds that are occurring between two adjacent atoms in order to form a larger structure called a molecule. That being said, we can also have bonds that form between molecules that already exist. So for example, let's look at this picture right here. This is one molecule. We'll call this molecule A. We can see that there is a covalent bond that is occurring between the atoms in this molecule A. And then we have molecule B. And again, molecule B is held together by a covalent bond, okay? So these are bonds we already talked about, but then you can also see that there is a bond that is actually holding the two molecules together, a very weak bond that's present between them. We see this a lot in biology, that sometimes these bonds can form between adjacent molecules, and we can even see sometimes that there are bonds that can occur between large molecules, such as what we see down here. Okay, this is a picture of a protein, and it's really large compared to what's up here. The two molecules above are only comprised of two atoms, whereas this protein, at least the section we're looking at, is comprised of quite a few. I have not counted exactly how many little atoms there are, but it's a lot. This structure is large enough that we can start to see interactions occurring between atoms in one piece of the molecule and atoms in another piece of the molecule. So for instance, look right here, this line is occurring between one portion and another portion of the molecule. And it's helping give the molecule its shape. Some of the types of bonds that kind of fall under this category of attractions within or between molecules would be hydrogen bonds, disulfide bonds, van der Waal attractions. Given the time constraints of the class, what we're going to do is we're really just going to focus on the hydrogen bonds and close it out there. Hydrogen bonds are attractions that occur between two molecules, or it can occur within a large molecule. But it occurs when you have a hydrogen atom that is forming a polar covalent bond with another atom that's much more electronegative than itself. Because hydrogen is a bit weaker than some of the things it bonds with, it tends to be the partial positive of a polar molecule. When there are two molecules side by side that are polar, they have opposite partial charges that can attract to each other. A really good example of this is what we see within water. So we have two water molecules right here. Let's see, here is water molecule number 1. And here is H2O number 2. So 2 water molecules. Each water molecule is held together via polar covalent bonds. Okay, so both of these guys right here, these are polar covalent bonds, uneven sharing that's occurring between oxygen and hydrogen. And as a result, it's going to cause partial charges. The hydrogen ends up being partially positive, the oxygen is partially negative. The same is true of the nearby water molecule. Here's the thing, opposite charges attract. So the partial positive of this hydrogen can be attracted to the partial negative of this oxygen. And it's going to form this attraction called the hydrogen bond. These attractions that occur between molecules are much weaker than any of the attractions that occur between atoms within a molecule. But they do hold together adjacent molecules, and they do require some quantity of energy to break. Individually, they are very weak. When there are a lot of them present in a given area, they can constitute quite a bit of energy in order to break a large number of them.